Hi everyone, good morning. My name is Samira, I'm an engineer at Wise, and here with me my teammates Yash and Idon. Today talk about is going to be we're from the database platform team at Wise, which is responsible for building a database, a platform to manage databases at scale and enabling self-service. Today's talk is going to be about how Temporal is helping us achieve this mission. Is this changing? Yeah. So on this day, Wise's journey began with the first commit that created a tiny app which allowed few customers to make money transfers. Over time, though, this tiny app, along with its database, grew in size that it became difficult to work with and challenging to maintain. In 2014, the decision was made to break it apart and transition to the microservice architecture. This architectural shift allowed the system to scale to what is now Wise, having over 16 million customers. However, it also led to a substantial increase in the number of databases. In fact, today we have over 450 of them in production alone, processing over 2.5 million money transactions a day. So given this scale, you can imagine how critical this database is, this infrastructure is to the business. If one critical database has a blip or is down, that means that our customer would not be able to view their balance or initiate a money transfer. A database is nothing but a software running on a server, and I assume the majority of you here deal with software, build software in your day-to-day work. And you would know that to make it reliable and ensure its optimal performance, you would need maintenance. One of the most intensive and risky type of maintenance is a database version major upgrade, akin to upgrading your laptop's operating system. It can lead to outages and potential data loss, corruption, or even data loss. We run the majority of our database estate on Amazon Relational Database and RDS for short, and I'm going to hand it over to Yash to talk us a bit through the challenges that we face with this service.
As Samira mentioned, that we use RDS for almost all our databases, about 90% of them. And it works great for most of the cases, but for a lot of our use cases, such as doing in-place upgrades, be it major or minor, or doing some instance resizing or right-sizing, we have to basically incur a downtime. And this downtime can be from a minute to several minutes. And this does not really play well with when we have 450 databases, because when there is a downtime, we sort of have a direct impact on revenue, and it also takes us away from our end goal of basically moving money cross-border instantly. Like when we define instant, it's like a transaction from source currency to target currency happening within 20 seconds. So when we in order to overcome this limitation of RDS, we have basically a need of faster some mechanism that we could basically do these operations without having a downtime. So we have developed our custom tooling, which uses basically an additional replica to perform these operations without any downtime, which basically which we call it as switchovers. Now, switchovers are basically done using a green environment. So you have your service, you have your service talking to a primary database. So instead of performing all the operations such as upgrades on the primary database, we go and create a green environment, which is where we do all the operations. And once we are happy with this, we go and shift traffic to the secondary instance. So let's see how this works, though. This is pretty similar to how we do zero downtime deployments with microservices. In traditional microservices, we bring up new pods with the new version. We then start sending it some traffic. Once we are happy, we start draining the connections from the older instances. But now what happens when we try to do the same with databases? If we just send traffic to the new database, what happens is we might be in a situation where we have split brain. So we can't follow the same approach there. So what we do is, instead of sending traffic, we first kill the connection, and then we basically point the application endpoints to the new database, and then re-enable traffic on that database. The diagram might show that this is a multi-step process, and it might take long, but this usually happens within a second, and in worst cases, we might go to a few seconds depending on how busy the database is. So this has basically worked for Wise for a very long time. We have been doing this for over 4 years, and over time, we have even built additional capabilities such as reverse replication on it. So let's say you did a switchover to 15.x, and what happens like after the switchover that you do not get the desired performance, or you encounter a bug that was not caught in staging. So we have a fallback mechanism where we could go back from secondary to the primary. Basically, we can repeat the process and go back to the previously working version of the database. Now, why are we here though? We have this process working fairly nice over 4 years now. The real bottleneck is in how we create the replica. Each database, basically, each green environment that we create requires a bunch of steps. And if you see this, we use industry standard Terraform Atlantis sort of GitOps workflow. And this used to work fine when we were having few databases, but at 450 databases, this process is basically a bit tiresome, and we'll see how. Let's see if you have a service talking to a primary database. Now, this primary database is on 12.x version. So we want to basically move to 15.x. What would be the process to create a standby replica? The first step would be you go to the Terraform, you clone the repository, create a Terraform pull request, and then create a replica, which is basically an RDS replica, which is also on 12.x. So you can't really directly jump and create a 15.x replica. That is not how RDS works. So once done, you go and you need to perform a minor version on it. So that is another pull request. It can take anywhere between half a day to, it can take anywhere between 30 minutes to half a day, depending on how big the database is. So the replica creation might take some time, and after that, you need to upgrade it to 12.y. Why 12.y and not 15.x? Because each RDS Postgres major version, you need to basically have an upgrade path. You can't just directly jump from any version of 12.x to any version of 15.x. Once we do that, well, you can't really still upgrade the replica because there's no way you could do a major version upgrade on a replica, which is on an AWS RDS replica. You need to basically promote it to a standalone instance. And when we want to promote it to a standalone instance, you break the replication. So in order to do that, we use our custom CLI-based tooling, which our database engineers use. So far we have done 2 pull requests, 1 custom CLI tooling execution. This basically also kicks off a timer on the RDS primary, where we have to basically, once we are breaking the replication, we need to start accumulating the transactions that are happening so that we can, once we have done the major upgrade, we need to basically sync those changes also. We don't want to lose any transactions. So finally, it's time to perform the major version upgrade. This would be another pull request. Someone will approve, maybe instantly, maybe half a day, and then you would be having 15.x. But it still requires a lot of CLI tooling, CLI command executions to basically finally set up the replication, because we were accumulating changes so far, but once the operations are done on the secondary, we need to make sure that those changes are also streamed and available on the secondary instance. And finally, after doing all this, we might have a green environment that is pretty much ready to switch over. At this point, the database engineers also perform additional operations on the secondary, such as vacuuming, which is basically a way of saying that, hey, vacuuming and analyzing, which is telling that, hey, update the statistics on the database so that once we shift the traffic, we do not face any slow queries. And all this takes anywhere between half a day to multiple days, depending on how big the replica is and other priorities of the database engineer. So once we are at this point, do you think, are we ready to switch over, Samira?
No, unfortunately, no. We got caged. The replication broke, and it couldn't be salvaged. We have to scrap this database and start over again. It means that it's going to wipe out all the effort and time that we spent preparing the standby database. Now, let's think bigger picture. We had around 40 critical databases that were due for a major version upgrade. Upgrading just one database takes the following: over 20 steps, manual steps, that carried high mental load and needed to be executed sequentially and only allowing us to perform 2 to 3 upgrades at a time. It could take days. It also required coordination with teams, from like sending Slack messages to sitting in Zoom meetings. And last but not least, the complexity of the process was so high that it couldn't be distributed to other like software engineers in the team. It needed to be done by a database engineer. With all this in mind, 40 upgrades would have taken us a quarter, which meant that we would basically miss the end of life deadline of the version that we were running. So the way, this is not sustainable, it's not scalable long term, and the way forward is to streamline and orchestrate this process as much as possible, if not all of it. The goal here is to think of databases not as pets, but more like cattle. So Temporal comes to the rescue with its ability to, with the ability to create workflows where you orchestrate various steps and activities. We started chipping away at those 20 steps and created our workflow that takes care of creating and preparing the standby database. This allows us to theoretically have an unlimited number of standby databases ready to be switched over. This also allowed our database engineers to focus on validating the process rather than running it. So this workflow, for example, starts off given an input, which is basically just a target database that the primary database that we're targeting, along with some metadata. It would start with running some basic checks, for example, that this database, this replica that we were trying to create actually does not exist, and the primary that we want to create a replica for actually exists. So some sanity checks against AWS. And then from there on, starts creating all the resources that come with the database. So that's around, like in our case, like around 20 resources from security groups, CloudWatch metrics, etc. And then once that replica is ready and available, then we start performing all the steps, the changes that we want to do, as Yash explained earlier, from performing a minor version upgrade and setting up the logical replication, performing major version upgrade, etc., etc. And then once it gets all the way to the end, it just blocks. It waits. Waits for what? A signal from a database engineer that everything looks okay and it can terminate successfully or actually finish successfully. So we like this because it still allows some human oversight over this process. So it's not fully automated, but maybe once we gain confidence, we can transition to that. And that confirmation is done through a signal, as you can see over there. So if it's a positive signal, that means that it's gonna finish successfully. Otherwise, if it's not, or something goes wrong in the middle somewhere running those steps, then we have Saga to the rescue. It would just perform like the compensations from like undoing all the changes that we've been made and cleaning up the resources. Now, with this workflow, plus some improvements that we've done elsewhere in the process that are not really related to Temporal, we managed to improve the process and make it a lot more efficient. It now only takes 9 steps, and we reduced the dependency on teams to only a minor dependency on one team. And thanks to investing in observability and monitoring, we managed to make it a lot more accessible to a point that a software engineer in the team can perform this upgrade. This process now has allowed us a couple of weeks ago to perform 40 critical major version upgrades in one day without any incidents and no downtime. Now, I'm going to hand it over to Edon to give you a sneak peek into our architecture and how we integrated with Temporal.
Hello? Oh, nice, it works. All right, yeah, let's dive into how we've deployed Temporal and implemented it within Wise. All right, there we go. This is a high-level diagram overview of how we've used it. Within Wise, as Samira mentioned, we have a microservice architecture, and Kubernetes is our container orchestrator. We've opted for using Temporal Cloud as the managed service for the Temporal service. This has enabled us to focus much more on the business logic of actually implementing the workflows, as opposed to having to worry about all the extra work that comes with having to do it self-hosted. We have clients and workers deployed as Kubernetes services. They're in 2 separate deployments. And we have segregated environments representing the different deployment environments that we've got within Wise, so development, staging, and production. And each namespace has its own MTLS certificate, meaning that workers and clients in the respective deployment environments can only act on their own namespaces. To zoom into this a little bit more, this is a bit of a more detailed overview. As I mentioned, we have clients and workers. The client is a UI self-service tooling that we've developed within Wise. This allows product engineers to interact with their databases and do some minor maintenance. And as part of this switchover work, we wanted to increase accessibility. And we've integrated the ability to trigger the workflows by DB admins from this UI, and also send some signals and queries. We have one task queue per namespace, and any communication that happens to Temporal Cloud goes through our VPC endpoint. We have our own private network connected to Temporal Cloud. Everything that leaves and goes into each worker and client is encrypted using a custom payload codec. We have decided to go with Fernet as the encryption algorithm. We've done this because Fernet is available in various languages and SDKs. So our client has been coded in Java, and our workers in Python. So we had to find something that we could adopt on both of them. And finally, we have interceptors. Interceptors, I don't know if you're familiar with them within Temporal, but they act as a middleware component that allows you to hook into parts of your workflow and activity executions. So if there's any activity failures, workflow failures, we can enrich the error messaging and alert back on our alerting system that we've got. Alrighty. All right. In terms of Temporal adoption, I couldn't help myself, sorry. In terms of Temporal adoption, these are some of our numbers in the past 4 months. You might think, depending on your usage of Temporal, you might think these are fairly low numbers. We have about 500,000 activity executions and 75,000 workflow executions. But despite this, we've been able to achieve massive impact on the business. As you've seen throughout this talk today, we've been able to automate a lot of our maintenance tasks, allowing DB admins to focus on other tasks and offload this really tedious manual process. We've got 5 workflows in production at the moment. Some of them have also contributed to business impact. One of them, for example, is an automated restore workflow we've got for databases, where we perform weekly restores to test how long it takes to restore a database in scenarios of a disaster. So you're thinking low numbers, high impact. We've learned something. And we'd like to share some of those learnings with you in case you try to embark on a similar journey, and we can save you some time. So through the process before we embarked with Temporal was quite manual, as you've seen. It included over 20 steps, and it could only be done by database admins because they had the most context. With Temporal, we were impressed by the ability to convert those manual scripts and commands that would be run on a database into a workflow. All we had to do was convert those Python functions or database commands into activities. We were already using imperative implementation, and all we had to do was convert into activities and orchestrate everything through a workflow. The other thing that we leveraged from Temporal was the use of signals, updates, and queries. This allowed us to have oversight over how the workflow was progressing and the activities. And we needed that oversight at first to build the confidence we needed in Temporal to then adopt it further on wider in the business. The stateless workers, we really leveraged the ability for the fact that workers don't have an application state and we don't have to manage it. This simplified our deployment of Temporal, as you've seen. All we had to do was set it up with Temporal Cloud and deploy the workers as Kubernetes containers. It was really straightforward, and as I said, it allows us to focus on business logic. Not having to care about application state means that when we deploy a new version of our code, we don't have to worry about the existing running workflows failing. Our code has to be deterministic. It has to be idempotent. We don't want things to crash, especially when it comes to a database upgrade. As you've seen, if any downtime can be potentially very critical for Wise, and this allowed us to develop really fast and manage all those exceptions that we inevitably ran into with retries. And yeah, if part of the workflow fails, as long as as the code is idempotent, we can replay up to the failure and just continue going. We had to also ensure that infrastructure was not duplicated, recreated, or overwritten. As you've seen with the replica creation, it involves many steps that create infrastructure on AWS. And if the workflow fails, we could just use the compensations to undo those actions that we've just done. It wasn't all smooth sailing, though. There was a bit of a learning curve with using Temporal, some of you may be familiar with. We were impressed by the documentation, the SDK examples, and the questions on the forums. We found that there were loads of examples that we could use straight out of the box. However, some SDKs had different examples than others, so we had to sometimes translate from languages that we weren't familiar with to try and use features. One of the things we ran into, especially for our long-running workflows, was the non-deterministic errors, which we had to wrap our head around. And as I mentioned earlier, we had to make sure that our code is idempotent so we don't recreate resources. When it comes to creating infrastructure, we had a lot of verbose code to actually interact with the AWS APIs. We had to deal with all the edge cases of potentially recreating the same resource or a resource that already exists. So all these different cases where something like Terraform would already warn us, oh, you can't recreate that resource, we had to now manage manually. Well, not manually, but implement it as code. And one last thing I'd like to mention again, make sure you use an encryption algorithm that is available between multiple languages and SDKs. We ran into some blips, even with the one that we had, but if you're just starting out with Temporal for the first time, stick to one SDK, as it will probably make your life a little bit easier. And finally, where do we go from here? Our journey with Temporal is not over. This isn't the last thing we're doing with it. As we've mentioned, the majority of the presentation that's been today has been about the replica creation. This involved creating all the infrastructure, and then performing the switchover was actually still a manual step, which involved some intervention. We'd like this to be a fully automated end-to-end process that could be triggered by potentially even product engineers without any oversight from us. As we move things into Temporal a little bit more, we'd like to have maybe more of a control plane where we manage our infrastructure and database lifecycle through Temporal as well. Perhaps where a workflow represents the entire lifecycle of a database, and we can perform actions on those. Terraform has limitations in that it is not dynamic to our needs, and we can't interact with it, integrate it with APIs, with internal systems. So at least with Temporal, if we manage our database lifecycle through a workflow, we can still interact with it through queries, updates. And lastly, as we continue to develop with Temporal, we're already starting to build some confidence in other teams that this is a very useful and powerful tool. We've received some requests to go to some talks, so we're building interest within the company, and hopefully we can increase adoption of Temporal in our teams and the wider engineering, platform engineering tribe. And that was it from us at Wise. If you've got any questions.
Okay, we have time for a few questions.
You guys want to come up as well?
Yeah.
You have the mic, right?
Yeah.
Hi, great talk. You mentioned that there were still several steps that couldn't be automated or that weren't automated. I'm curious as to what was the decision criteria for not automating those?
I think it's the last step where we actually shift the traffic. It has to happen within a second. That is the fastest like that is the lowest downtime that we are seeing with our current executions. And since Temporal has a distributed nature, we are still trying to figure out what would be the best way to sort of do this step. And there are also human elements in this, basically expertise of database engineers on when to trigger the switchover. They know which service and which database are best suited for, let's say, switching over at 2 p.m. They know the workload patterns. So currently we rely on their expertise, but we are trying to bake all those knowledge using metrics to sort of say that, okay, now is a good time to perform a switchover. You know?
So you said that you were using manual runbooks, and now you've automated that. What kept you from automating that before? Had you tried to automate it with other technology before? That's really the main question, is what enabled you to automate that now?
I think we were, as you saw, the replica creation itself, it can take anywhere between some time, like 30 minutes or to half a day, depending on the storage size and so on. It also had this, we had this strong requirement that all our changes are basically version controlled and managing the infrastructure through Terraform, basically infrastructure as code. So we basically needed a convincing way to say that, okay, we can do this without having to have our entire process be driven through Terraform. So that is where we started looking out for different engines. We evaluated a couple of them. Cadence was the first one, I think. We also saw step functions and SWF from Amazon. But Temporal was like the one that checked all the boxes, and we went for it.
One quick follow-on question. You're still using Terraform in places, or have you replaced it?
It is still there. We have it in parallel. Our plan is to basically have all the static things in Terraform, such as security groups, networks, and those things. But the dynamic things should be shifted to Temporal.
Any others?
Yeah, well, my question is about the interceptors that you created. I'm wondering what kind of observability you achieved while introducing the interceptors and how that complemented the level of information that you had already with Temporal.
So can you repeat the question, please?
Yeah, what kind of observability did you gain while introducing the interceptors in the workers?
Yeah, so the interceptors here didn't really, it's more about just making sure that getting those alerts in case activity fails or a workflow fails. That doesn't really help. It's unrelated to the workflow or rather the improvements elsewhere that we introduced in the process that allowed us to make it a lot more accessible. So that's the observability that I mentioned earlier was more about, in order to basically reduce the dependency on the service teams that actually own the service that connects to this database, we introduced this a DynamoDB solution, that acts as a central store for the database configuration. Okay, this service uses this database, and this is the host that it needs to connect to. And through some given it's a Java house, we have a common library for how to connect to a database. So we implemented a solution in there, or some other teams have helped us to implement a solution in that library so that it can actually pick up the host from DynamoDB. And so once that library would emit metrics, we have dashboards on top of those metrics. So we can, instead of actually waiting for the service teams to confirm to us that, hey, yeah, I'm connecting to this database, we can just look at the dashboard that tells us that, yeah, this is we're seeing activity in this other database, and it's okay to proceed to switch over. But interceptors in the workers that are not really related to the observability.
Yeah, the interceptors were just to get us alerted if an activity or workflow fails, so we don't have to monitor the dashboard all the time, as in the Temporal dashboard.
One more question.
Hi, what frameworks did you use to evaluate the cost of using Temporal Cloud versus how frequently you're doing these database operations? Is it constantly doing maintenance, or do it a few times a year? What does that look like?
I mean, we know we're at a replay talk, but you saw our usage numbers. So for Temporal Cloud, our bill is not really high. And the savings that we make in terms of engineering time are much greater. It allows database admins to focus on other improvements that we can do in our infrastructure as opposed to having to do this toil work all the time.
Yeah, and switchover process is not only done when we need to do a major version upgrade. We would need to do it for a minor version upgrade as well, which is a lot more frequent than a major version upgrade, but also for things like a schema change on a critical database. Because, for example, indexing a column in a table that has like billions of rows, that can lock the table and bring it down, or bring the database down. So sometimes we have to actually spin up an entire standby database, make that index or schema changes in that standby database, and then switch over to it. So for that, we need to switch over process. And obviously, so we're not going to be using Temporal just for this workflow. We can have so many other workflows to build. Speaking of the runbooks and that we and automate, I guess some other automation that we have so many Lambda functions that are just running everywhere in AWS, and we would like to port all of those to workflows so that they can be centralized in one place. And they're all workflows, so we don't have to find, kind of just scattered everywhere in different repositories and lacking any monitoring or observability. And also running a workflow, having a workflow running in a worker in our Kubernetes and service mesh means that our workflows are going to be a lot more smarter than a Lambda function, because it can interact with other services in the mesh in Kubernetes, rather than when running a Lambda function in AWS, it's not going to be able to talk to any service in the mesh.
Okay, well, let's give them another round of applause.